Hello my dears, how are you all? So in the last class we discussed about what we discussed in the last class. Some important problem regarding the circuit theory, especially some series and parallel combination and some typical circuits, right? So we almost wind up the circuit theory. That means we completed one subject. So our mission is to complete all the subject, right? So definitely I will do that. So I completed circuit theory. I think you got a grip right now. You got a grip right now in electrical engineering, because circuit theory is the basics of all the subject. Because in many subjects like a control system or power system, you may face some problems like in Thevenin's equivalent circuit, or electronics also, Thevenin equivalent circuit, Norton equivalent circuit, right? And the temperature dependent, something like that, the combination of the resistance and inductor and capacitor like situations, many situations are there you may face in future, in the subjects. There we can apply circuit theory. So what I am trying to say is circuit theory is the very basic of all the subjects in electrical engineering. All the subjects in electrical engineering. If you learn circuit theory in smarter way and you have to solve a question, at least you have to try a question, you can try a question, then it is very easy to cover the remaining subject in electrical engineering. Okay, so today we are going to take a new subject. It's a very interesting subject. I know you all, you all waiting for that subject. It's nothing but electrical machines. Electrical machines. I know you are expecting the subject because it's very interesting, and most of the question, I think 30 to 40% of the question in any examination, you may find this subject, right? Machines, from machines, that is from machines. So first I am going to take about transformers. And slowly we can move to other machines. Okay, so what do you mean by a transformer? What do you mean by a transformer? So transformer is a static device, right? It's a static device. Transformer is a static device which is used to step up or step down voltage. Step up or step down voltage. And since it is a static device, the efficiency of the machine, that is nothing but our transformer, compared to all other machines, because whenever we are going to dealing with AC machine, DC machine, like synchronous machine, AC machine, DC motor, alternators, like that, definitely there are moving parts. So definitely a part of the energy that we are given to the system or to the motor or to the machine is lost as heat or something like that. Okay, that means the efficiency of the all remaining machines except transformer is very less compared to transformer. So the efficiency of the transformer is in the range of efficiency in the range of 95 to 98%. That is the main advantage of using transformer. So it is a static machine. Static means it is not moving. There is no moving part in the transformer, so that the efficiency is very high. And all of you know the working principle of transformer, right? Working principle of transformer is nothing but what? Mutual inductance. So this is the working principle of a transformer. Briefly I will explain the transformer working principle. Briefly I will tell you in brief. So this is nothing but primary winding, and this is nothing but secondary winding. Suppose N1 and N2. Suppose we are giving an alternating voltage V of t as the input. Due to that, there is a flux which is surrounding the coil number 1 or N1. A portion of the flux is also linking with coil number 2 or N2. Okay, this is called the mutual flux. This is called the mutual flux. Mutual flux. So, by Faraday's laws of electromagnetic induction, whenever we are giving an AC side, AC voltage, which is time varying in nature, that means which is in the nature like this. Which is in the nature like this. It is time varying in nature. What happened at every instant its value is varying, right? So, whenever its value is varying, the magnetic field produced, that means the current also what sinusoidal in nature, right? If the voltage is sinusoidal, means the current also sinusoidal in nature. If the current is sinusoidal, the flux produced around the coil number, that is N1, is also sinusoidal. So due to Faraday's laws of electromagnetic induction, there is an self-induced EMF in the coil number 1, that is N1, which is nothing but E1. And that E1 will be directly opposed to the applied voltage V of t. Okay. And a portion of the flux is also linked with the number 2, that is N2 number of conductors. So there is a chance of producing EMF in the secondary terminals or second number of turns, that is N2 also, due to same Faraday's laws of electromagnetic induction, and that also opposes the applied voltage. That is called the E2. So depending upon the number of turns in the secondary, that is N2, with respect to N1, we can increase or decrease the voltage, because according to Faraday's law, the EMF inducer is directly proportional to N into d phi by dt, correct? Or simply E is equal to N into d phi by dt. If you increase the number of turns, then EMF will be increased. That is the principle of the transformer. If you make an arrangement in such a manner that what voltage you expect, you are going to expect what voltage you are going to expect. So depending upon the voltage, whether it be step down or that means high voltage, or whether it be low voltage, you have to make the number of turns accordingly, so that definitely there will be the output according to that number of turns, which may be step up or step down. If the primary voltage, compared to the input that we applied, if the output voltage is higher, then it is called a step up transformer, and compared to this V of t, if the output voltage is less, then we call what? Step down transformer. Okay. So in step up transformer, V, or I can say that E2 greater than, suppose this is E2, right? E2 greater than V of t, or simply E1, that is also, but I2 less than I1. That means, I will explain. Transformer is a device. It's a transformer, means nothing but transfer of power. Transistor means transfer of resistance, right? Similarly, transformer means transfer of power. That means the input kVA, that is V1 I1 in the transformer, will be equal to the output kVA V2 I2. That means there is no change in the power of a transformer. If you are given a 50 volt ampere to the transformer, definitely the output will be 50 volt ampere for ideal transformer. Practical, there may be small losses, but definitely it will be 49.9 or 49.8 something. But we are doing calculation in accordance with input kVA. This V1 I1 is nothing but input kVA. This V2 I2 is nothing but output kVA. So the input kVA and output kVA are equal in a transformer. And we have a voltage and current relation as, suppose, I will explain the working of transformer. Okay, definitely I will explain the working of transformer. So that's all for the basics of transformer. Okay, I will explain the voltage transformation ratio and all in working of a transformer. And there are two types of transformer depending upon the construction. Depending upon the voltage, there are what? Step up or step down, that we simply explained. So I will complete this. So the voltage equation of a transformer is nothing, you know this, right? So no need to confused and all. E2 by E1 equal to N2 by N1 equal to I1 by I2, which is nothing but K or transformation ratio, where K is known as the transformation ratio. Transformation ratio. If the value of K is greater than 1 means it is a step up transformer. If K less than 1 means it's a step down. Yes, step down transformer. Step down transformer. That means if E2 greater than E1, only K will be greater than 1, right? So the peculiarity of this equation is E2 by E1 equal to N2 by N equal to I1 by I2. The current relation is reversal of the voltage relation or number of turns. That you have to note all this time. Okay. So the input kVA will be equal to the output. These all are basic, you know this. Definitely you know this. Transfer of power is nothing but the input to volt ampere will be equal to output to volt ampere. So the relationship V1 by V2 will be equal to I2 by I1. From this it will be obtained. We will obtain this, right? From this we are obtaining this. E1 I1 is equal to E2 I2. That same concept. So E2 by E1 will be equal to N2 by N1 equal to I1 by I2. Where E2 is nothing but the secondary inducer voltage, E1 is the primary inducer voltage, N2 is the secondary number of turns, N1 is the primary number of turns, I1 is the primary current and I2 is the secondary current, and which is called the K, okay. And depending upon the construction of a transformer, there are two types. Construction wise, depending upon the construction of a transformer, there are two type of transformer. First one is core type and next one is shell type. First one is core type and next one is shell type. Let's see one by one in brief. Okay, one by one in brief. Actually, I am taking very important points only, because if you want to take this transformer up to 6 months also you can take this subject, single subject transformers. That much content is there actually. But I am taking classes with respect to or in perspective of our examination point of view, right? So many things you may study in beta classes, no, that may not see here, but many things you didn't study there, sometimes you may see here also. So that is the main thing. Okay, I am not focusing on very much on theory part. I am focusing on the concept plus the equations plus the problems. That is the main thing we need. Theory automatically come, right? If you do some problems, automatically you will learn some theories along with that. Okay, so no need to waste time for doing vast or very long theory sessions. It will be really boring to you and me. Okay, so first we have to see core type transformer. Transformer is T bar F, simply you can write that also. I am not a good drawing artist. Okay, this is the rough figure of a very rough figure. Okay, I know that. This is not a perfect figure, I know, but okay. So this is a core type of transformer, and core type of transformer is used in high voltage transformers. High voltage transformer, and there are a portion of the core is said to be rectangular in nature, or for theoretical, actually for theory, it is said to be circular in cross section. The core is actually said to be circular in cross section, but this is the shape, but the cross section will be circular in manner. But for practical cases, in order to make a circular cross section, right, it is very difficult, because we have to measure the radius and uniformly we have to create the section. So in order to make a circular cross section throughout the construction is very difficult. That's why we are using stepped core. Stepped core. Stepped core means in the form of not perfectly a circle, but a step like structure. No, step like that, like this is said to be somewhat in the manner of a circle now. That is why it is called a stepped core. So stepped core we are using here because of difficulty in making a perfect circle throughout the construction. It have two parts. One is yoke. The horizontal section of the core is called the yoke, and this main section is called the core or limb. And on the core or limb we are winding the primary as well as the secondary winding. So the thing is that a part of the primary, that is of course what it may be, suppose it is a step up transformer, you assume LV winding is always connected in near to the limb or core. The purpose of doing such arrangement is that in order to reduce the insulation, because when we are using a LV winding on the surface or near to the surface of the core means we need less insulation for that. If you are using high voltage winding near to the core means in order to separate it from the core you need a very high type or high insulation, high cost insulation. So in order to avoid that we are using a low voltage winding always near to the core. This is one question. And a part of the or half of the primary is and half of the secondary is wound on the same core. This is because in order to reduce the leakage flux. That means in the figure, in the transformer figure, this is primary and this is secondary. This is just for the understanding purpose. But in practical case, if you keep these two windings this much apart, then there will be a lot of leakage of fluxes. The transformer efficiency will be reduced. That means many of the fluxes produced in the primary will lost when reaching to secondary. It will not reach to secondary. So the mutual inductance action will not be perfect there. That is why we normally wound half of the primary and half of the secondary on the first limb, again half of the primary and half of the secondary in the second limb, so that the leakage flux can be reduced very much. And this is called nothing but the mutual flux phi. And this is all about the core type of transformer. That means it's very simple construction actually. It is used in high voltage transformer, and repairing also very easy, right? Repair is very easy because all the windings are in side limbs. So if you open the side limb, you can simply repair the transformer. So this is used for high voltage transformer, and in low voltage, in not very low voltage, but compared to the very high voltage, in low voltage transformers, stepped core means in the form of square or rectangular stepped cores are used. Normally circular stepped cores are used there, not perfect circle, but in the form of a circle, nearby circle. Maximal circular form will be used, but stepped core will be used. That you have to remind all the time. And the purpose of using stepping is also, actually it is very advantageous, that we will discuss when it demand. Okay, the construction side, when we will discuss construction side or winding session, definitely we will discuss that also. Okay, so that all about the core type transformer. And let's see what is a shell type transformer. What is a shell type transformer? What is a shell type transformer? See the winding. See the peculiarity of winding here. See the peculiarity of winding. So shell type transformer is normally used in low voltage transformer. Shell type transformer is normally used in low voltage transformer. See, in our home now, radio or TV, I mean not TV, radio or a VCD player or DVD player, old VCD or DVD player, no, in that there will be a transformer, right? That is actually a shell type transformer. So shell type transformer is used in low voltage application, simply your low voltage application. Low voltage application. And there are two limbs are there. One is called the central limb and two side limbs. The area of cross section of the central limb is double as that of the area of cross section of the side limb. So that the flux in the central limb is, suppose this is phi m. This is phi m is divided into two parts like phi m by 2 and phi m by 2 in the two side limbs. And the winding is on the central limb. The winding is on the central limb. And this is also a special type of winding. See, one portion is LV and other is HV, and one is LV and other is HV. If you see this, you can see between two HV winding there is an LV. Between two LV winding there is an HP. That means this type of winding is called sandwich winding. This type of winding is called sandwich winding because in between two HV windings there is one LV winding. It is like a sandwich, right? Sandwich means something in between two, right? That is called the sandwich. So sandwich winding is used here, and the peculiarity or the problem with respect to this type of winding is that the repairing is very difficult. Repair is very difficult. Repair is very difficult because if anything happened inside the coil, the whole transformer should be what? Break. I mean to be broke in order to get the windings outside. So the repairing of this type of the shell type of transformer is very difficult when compared to this core type of transformer. Once it is damaged means it is simply damaged. We don't try to repair that. It is very easy to remove that and buy a new transformer. That much difficult is the repairing. That much difficult is the repairing. Okay, and which is used in the low voltage equivalent bus. That's all. And the area of the central limb is double as that, because more flux is carrying in the central limb and the areas will be double as that of the side limb. That's all for shell type transformer. That's all for shell type transformer. Just a brief idea. Okay, so that's all about the construction of our transformers. Construction of our transformer. Next we have to see in detail of working principle of transformer. In detail working principle of transformer. Working principle of transformer. Working principle of transformer. Working principle. I have already told you that mutual inductance is the working principle. Mutual inductance is the working principle. See, I already told you the working, but some more details I have to give you. So that is nothing but when we are giving an input voltage which is sinusoidal in nature, there will be of course the current I1 which is also sinusoidal in nature, and due to that there is a magnetic field produced around the N1 number of turns in the primary, right? So due to the magnetic field which is produced in the N1 number of turns, according to Faraday's laws of electromagnetic induction, if this number of turns is N1 and there are changing flux happens, then definitely there will be an induced EMF, let be E1. It is nothing but minus N into d phi by dt. Minus N into d phi by dt. So minus N1 into d phi by dt here. So this is the induced EMF in the primary. And due to this minus sign, the meaning of minus sign is that induced EMF is opposite to that of the applied voltage. Even that opposite to that of the applied voltage. Okay, and definitely a portion of the flux which is common to both primary and secondary, which is called the mutual flux, and due to this flux also there is a linkage of this mutual flux on the secondary side also. That means there is a flux around this. A portion of this flux is linked with this N2 also, because it is changing. So the N2 number of turns, there will be also some induced EMF. That is induced EMF is called the induced EMF in the secondary. That also equal to minus N2 into d phi by dt. Minus N2 into d phi by dt, which is also opposite to that of the applied voltage. Applied voltage, which is also opposite to that of the applied voltage. And due to that there is a current I2 and there will be some voltage V2 across the terminal bus. So I want to mention one thing, this E1 is opposite to that of V1. That means V1 and this V1 is nothing but V1 of t and V2 of t. Okay, V1 and E1 are 180 degree out of phase. Similarly, V1 and E2 are also 180 degree out of phase. E1 and E2 are in phase. E1 and E2 are in phase because both are opposite, right? Both compared in these two means these two are what? In phase quantities. In phase quantities. That is, you have to note from this. And definitely that equation is nothing but E2 by E1 is equal to N2 by N1 is equal to I1 by I2 is equal to K, and the input voltampere V1 I1 will be equal to output voltampere V2 I2. This is very important. This is very important. So that's all of the very simple. You know the working, right? That's why I don't want to go much deeper into what is mutual interest and what is self-interest. No, I don't want that, because you already know this. So simple working of a transformer is that's all. Okay. Working of the transformer is that's all. Clear? And next we have to see the EMF equation of a transformer. Very important. EMF equation of a transformer. Very important. EMF equation of a transformer. See, since the voltage applied is sinusoidal, the current is also sinusoidal, and the nature of the flux produced also sinusoidal. Let B phi is equal to phi m sin omega t. That be equation number 1. So the induced EMF, in the primary E1 will be equal to, what is that, minus N1 into d by dt of phi, or we can say that minus N1 into d by dt of, what is phi here, phi m sin of omega t, or which is nothing but minus N1 into phi m into omega into cos of omega t. Or what is minus cos omega t? It is nothing but phi m into N1 into omega into sin of omega t minus pi by 2. That is nothing but minus cos omega t can be written like sin omega t minus pi by 2. Okay. So this is E1. So this is nothing but this can be together right like Em sin of omega t minus pi by 2. Okay. So this is in the form of E is equal to Em sin of omega t minus pi by 2, because this together we can term this as Em. So the RMS value of the induced EMF in the primary, RMS value of induced EMF in the primary, I will write like E1 will be equal to Em by root 2, right? RMS value is nothing but ERMS equal to Em by root 2, you know sinusoidal quantity. That Em is nothing but N1 phi m omega divided by root 2. Correct? That is the RMS value, right? E1 is nothing but the R. Capital E1 is the RMS value. Small e1 is the instantaneous value. And which is nothing but, my dears, phi m, what is omega? 2 pi into f whole divided by root 2, which is nothing but N1 phi m 2 pi into f. This 2 can be write like root 2 into root 2. Is it any problem? No. Divided by root 2. 1 root 2 and 1 root 2 cancel. Root 2 is nothing but 1.414. 3.14. If you multiply that together, you will definitely get this one. That is the equation, EMF equation of a transformer. So the primary induced EMF, RMS value of primary induced EMF is nothing but 4.44 into F into phi m into N1, where F is the frequency, phi m is the mutual flux, and N1 is the number of turns in the secondary. Similar case for the RMS value of induced EMF in the secondary, what will be that? 4.44 into F into phi m into N2 bus this much volt. So this is nothing but the RMS value, right? This is nothing but the RMS value, right? Then what will be the average value? This is the RMS value, right? What will be the average value? What will be the average value? For that I have to introduce one term which is nothing but form factor. Form factor. Kf. Form factor is nothing but Kf is equal to RMS value divided by average value. That is the form factor. For AC, single phase AC, the form factor is given as 1.11. It can be derived using the RMS value. VRMS equal to Vm by root 2, average value 2 Vm divided by pi. Okay. If you do that for a single phase sinusoidal AC supply, definitely you will get 1.1. Oh, you definitely get. So, okay, I will prove that also. For again, RMS equal to VRMS equal to, suppose it is Vm by root 2. Average for full wave cycle is equal to 2 Vm by pi. If you solve this, you will definitely give 1.1. It is the form factor. Okay, RMS value divided by average value. So from this average value is nothing but RMS by 1.11, right? Average value is nothing but form factor, which is nothing but Kf. Average value is nothing but, what is that? RMS divided by Kf, right? So you have the RMS value, right? That is average value of E1 is equal to, what is that? RMS value, which is nothing but 4.44 F into 5m into N1, right? Divided by Kf is nothing but 1.11. If you do this calculation, you will definitely get 4 F5m, correct? 1.41 for 1.11 4 times you will get 4.4, right? So 4 F5m into N1. This is nothing, the average value, average value of inducer EMF. Similarly, E2 average also, what is that? 4 F5m into N2. That is the average value in the secondary. So this is a very important relation in transformer, because many cases where you can apply this, and you can apply this, I mean property also you can apply. Some of the properties are there with respect to this equation that I will discuss in the later session definitely. Whenever it needs, okay, whenever it needs I will tell. So that's all about the EMF equation for transformer, okay. And let's do some important problem regarding this EMF equation, connecting this EMF equation, okay. Write a problem. Very easy problem. We can start with very easy problems, and slowly we will increase the level, okay. Slowly we will increase the level, okay. Okay, write a question. A single phase transformer has $350 primary and 1005 secondary turns. Primary means primary and secondary, like a short like this. The net cross sectional area of the core is core is 55 centimeter square. If the primary winding be connected to primary winding be connected to 400 volt 50 hertz single phase supply. Calculate one maximum value of the flux density in the core. In the core to voltage induced in the secondary winding. So this is our question. Carefully note the question. Carefully note the question. Okay. A single phase transformer has 350 primary. So N1 will be equal to what? 350 numbers. And 1005 secondary. So N2 will be equal to 1005 numbers. The net cross sectional area of the core is nothing but, that is A is nothing but 55 centimeter square, which is nothing but 55 into 10 raised to minus 4 meter square. Always convert the standard to standard values, then only the answer will be smooth. If the primary winding be connected to a 400 volt supply, that is nothing but E1 will be equal to what? E1 will be equal to 400 volt. E1 will be equal to 400 volt, and frequency, of course, frequency will be equal to 50 hertz. So what we have to find? We have to find maximum value of the flux density in the core. First one, maximum value of flux density is nothing but Bm, right? Flux density is nothing but Bm. We have to find. That equation we can use for that. We have E1 equal to 4.44, that is RMS value. In problems, unless it is mentioned its average, we normally do with respect to RMS value. Okay. So 4.44 into F 5m into N1. Is it correct? This Bm is nothing but 5m by A, correct? Bm is nothing but 5m by A. Flux density is nothing but flux per unit area, right? Flux by area. So that this 5m will be replaced as Bm into A. So it will become 4.44 into F into 5m is nothing but Bm into A into N1, correct? Into N1. So from this Bm will be equal to E1 whole divided by 4.44 into F into A into N1, correct? F into A into N1. Bm will be equal to, if you substitute this, E1 is nothing but, it is already given 400 whole divided by 4.44 into 5 is nothing but 50 into A is nothing but 55 into 10 raised to minus 4, right? 54 into 10 raised to minus 4 into N1 is nothing but 350. If you do the calculation, you will have a value of 0.93. Unit is nothing but Weber per meter square or Tesla. Both are unit of flux density. Both are the unit of flux density. Simple, you just apply the equation. Flux density is nothing but Bm is equal to 5m by A bus, and you just the basic equation that we discussed in the previous session, the EMF equation. Just you applied that, you got the answers. So in the examination you may expect this type of question, because they don't want to trouble you, but they want to simply check your basic knowledge level, bus. Not in the RRBJU or SSCJE like etc. Some interview also. If you are going for some interview, if you are an MTech graduate, many cases are there. Suppose you are an MTech graduate, you may face a problem of interview. That means whenever you apply for a college, like for the post of assistant professor, they may check your knowledge. How can they check? They simply give some questions. They simply know you have to. They simply want to know what if you have a very good knowledge on basic. That's all. They don't want to derive the transfer function of that to second order low pass filter or high pass filter. No, that type of question they will not ask. They simply ask the basic questions. What is flux density? Interview also you may expect that type of question. What is the EMF equation of the transformer? Or what are the parameters on which that EMF equation lies? Depends. That type of question you may expect in your examination. So please take care of this. Okay. And what is the next question? Next part of the question. What is the next part of the question? What is the next part of the question? That is nothing but voltage induced in the secondary winding. That is right. that is nothing but E2, right? E2. Inducer in the secondary means E2. Load voltage is actually V2. Okay. So inducer is nothing but E2. So how can we find? You have simple equation, E2 by E1 is equal to N2 by N1 bus. What is E2 here? E2 is equal to N2 by N1 into E1 bus, which is nothing but N2 is nothing but what? 1500 divided by 350, right? Into E1, you found, right? E1 is equal to what? E1 is 400, right? 400. So if you do this, the calculation, you will definitely get the answer. (1200 volt). That is E2. That is E2. Okay. Okay. Is it clear? So that's all about the problem. That's all about that problem. Okay. So let's do another problem. Can I rub this? Can I rub this? Okay. Do another question. Let's do another question. A 3300 bar 250 volt 50 hertz single phase transformer is made on a core having a cross section area of a cross section area of 125 centimeter square and 70 turns on low voltage side. Calculate 1 BM and 2 N2 BM and N2. Okay. Okay. How can we solve this? First we have to write the written data, given data, that is E1 is nothing but 3300, right? It's a step down transformer, right? 3300 volt, and E2 is nothing but 250 volt. And F is of course 50 hertz, no doubt in that. Is made on the core having a cross section area of 125, that is A is nothing but 125 centimeter square, which is nothing but 125 into 10 raised to minus 4 meter square. And 70 turns on low voltage side, that is nothing but N2 is equal to 70, right? N2 is equal to 70. We have to calculate BM. So for connecting that BM, the only equation we have, E2 equal to 4.44 into F into phi m into N2, and again it is equal to 4.44 into F into phi m is nothing but Bm into A, right? Into N2, correct? So from this Bm will be equal to what? E2 divided by 4.44 F into A into. You have all the values, right? You have all the values. E2 you have, what is that? E2 250 volt. So N2 you have, what is N2? 70. So if you directly substitute this, no, 250 divided by into 50 into A 125 into 10 raised to minus 4 into N2. What is N2? 70. If you directly substitute, you will get the answer. Okay, you can do it in home. It is 1.28. Paper per meter square. You can do this in your examination. The terms now that will not be this much complicated. You can easily cross it. Easily cancel it. The numerator and denominator, you can easily find the answer. Okay. So in the examination, you may expect that type of question. This is just for the understanding purpose. Okay. And what is our next step? We have to find N2. Easy. E2 by E1 is there. What is we have to find? N2, not N2 actually. Yes, that question is actually meaningless. It is N1, not N2 beta, it is N1. It is N1. Okay. How can we find N1? Simple equation. What is that? E2 by E1 is equal to N2 by N1. Okay. You can easily find. So N1 will be equal to what? N1 will be equal to N2 by E2 into E1. So N2 is given as 70. E1 is given as 3,300 E2 250. You can cut this and definitely you will get an answer of nearly 924. Okay, I will do this. Okay, I will do this. Don't worry. So cut with 5, it will be 5, 5, 25 and 5 and 12, right? $14, right? 14. So again cut with that 5 into 60, 66 into 14, what will be that? 66 into 14. Correct, 924. So that is nothing but N1. That is nothing but N1. So N1 equal to what? 924. That is the answer. N1 equal to 924 is the answer. Okay. And let's see another session now. The problems are very easy actually. You can solve by simply doing applying the formula. No need to confuse, no need to headache, no take a headache, because it's very easy. It's very easy. So the concept of ideal transform. What is meant by an ideal transform? What is meant by an ideal transform? Ideal transformer has the following specialities. First one, primary and secondary resistance is 0 or very small or negligible. For ideal it's 0. For ideal it's 0. Primary as well as the secondary resistance is not there. That means whole of the energy that we are given can be utilized, so that there will not be any loss as heat. inside the winding, so that the primary and secondary resistance is 0. Next one, primary and secondary leakage inductance or flux or leakage reactance is 0. That means there will not be any leakage inductance or leakage flux. This is leakage flux or leakage reactance in the transformer. That means, what is the meaning of that leakage flux or leakage reactance? In a transformer, see, in a transformer, this is the transformer. Suppose a simple expansion transformer. The flux produced around this, some part of that flux is linked with this also. But some flux is not linked to secondary. That means a portion of the flux in the primary winding, it's not linked with the secondary winding. That is called the leakage flux. That is called the leakage flux. Or the reactance associated with that leakage flux is called the leakage reactance. Or the inductance associated with leakage flux is called the leakage inductance. So, due to that leakage flux, it's actually a loss, right? It is actually a loss, right? If there is no leakage flux, then all of the flux will be connected with the secondary. Then the efficiency will be very high. There is no loss. So, for ideal transformer, primary and secondary leakage fluxes will be 0. That means whole of the flux produced in the primary will be connected to the secondary. That is the meaning of that. And the efficiency, of course, will be equal to 100%. Efficiency definitely equal to 100%. That means there is no losses. No losses in the transformer. The efficiency will be 100%, right? The efficiency will be 100% then. 100%. So we can draw a equivalent circuit of an ideal transformer, like if you take the flux density or phi m is the reference. Why I take this phi m as a reference means phi m is common for, that is nothing but the mutual flux, right? Which is common for primary as well as secondary. That's why I took phi m as the reference. And there is a voltage called V1. And we know that V1 and phi m, no, definitely it will be 90 degree lagging. With respect to that phi m, the V1 is 90 degree lagging. And this is called the E1. And if this is a step up transformer, this is called the E2. And this is called the I, or simply I1, primary current I1. So this is the Phasor diagram of a ideal transformer. Phi m, definitely this phi m will be, because you know in the equation itself it's given phi is equal to phi m sin omega t. What is that V again? Did you get the induced EMF as E is equal to what? Induced EMF E1 will be equal to what? Induced EMF E1 will be what, madam? E1 will be phi m sin omega t minus pi by 2 na? Minus pi by 2, right? That equation of previous, check the previous equation. That induced EMF derivation, no? In that equation, we derived the equation for E1 equal to phi m into sin of omega t minus pi by 2, right? So that is E1 is this, E1. So E1 is lagging behind phi m by 90 degree plus. And E1 and E2 are in phase quantities. So I draw this. But E1 and V1 are opposite quantities, because directly opposite to the applied voltage is the induced EMF. That is why E1 180 degree out of phase with respect to E1, V1 will be 180 degree out of phase with V1 bus Kadam Khali. That is the ideal transformer Phasor diagram. Ideal transformer Phasor diagram. Okay. And this N1I1 is called magnetizing ampere turns, and N2I2 is called demagnetizing ampere turn, because N1 I1 is actually the responsible for the magnetization purpose, but N2 I2 means I2 is opposite to that of the I1, right? In the diagram itself it's clear. So I2 try to reduce the magnetic flux in the circuit because I2 act in opposite direction. I1 is, see, this is the diagram now. This is the diagram, right? So I1 is in this, that is I1 flows like this, but I2 is in this direction, means I2 like this. So I1 tries to maximize or magnetize the component, but I2 tries to demagnetizing the component. That is why N2 I2 is called demagnetizing ampere turns. N2 I2 is called demagnetizing ampere turns. Okay, and definitely there is an equation, you know this, kVA out equal to kVA in. kVA out is equal to kVA in. kVA is nothing but volt ampere. In terms of kilowatt, it's kilovolt ampere. Input, whatever power is given to the transformer as input in volt ampere, the output power also same. That means there is no losses. Transformer means transfer of power without changing frequency. Without changing frequency. That is the meaning of this kVA out is equal to kVA in. Okay, and what is the time now? Okay, so let's do one more thing now. Next, transformer on no load. Transformer on no load. This is the equivalent circuit of a transformer on no load condition. Why this equivalent circuit happens? Why you don't draw that secondary side? And why on only these branches are there, not the input resistance reactance are there? Okay, so this is the transformer on no load. Why this means? Under no load condition, the secondary of the transformer is actually open circuit. That is the meaning of no load. No load means the secondary side is open. That means there is no current flowing in the secondary side. So that there is only these parameter exist in the transformer. There are only these parameter exist in the transformer. Where V1 is nothing but the what? Applied voltage, right? Applied voltage. V1 is nothing but the applied voltage. Due to that there is a current I1, and I0 is nothing but the no load current, which is normally 2 to 5% of full load current. FIF. No load current is very low. It is not normally, it's in the range of 2 to 5% of full load current. IW is, what is that IW? It is called the working component of no load current, and IM is nothing but magnetizing component of no load current I0, and RW is called working resistance, and XM magnetizing reactance. These are very important parameters. So whenever you applied a certain voltage in the transformer on no load, the current drawn by it called the no load current I0. This no load current is utilized for two things. One, it is used for a small portion as in the heat of the core, as a heat of the core. That means whenever you supply some voltage in the transformer core, even though there is no load, means a small heat is generated there. The heat is comprises of eddy current loss, hysteresis loss and a small amount of copper loss. And due to that losses, the loss component of that no load current is called IW, and definitely loss in the form of heat means there should be some resistance. We can represent like a equivalent resistance, right? That equivalent resistance is called RW, or it called working resistance. Or this XM is nothing but it is the reactance which is responsible for the setup of flux in the core. For the working of transformer or for the working of transformer action, there should be some flux. There should be a flux setup in the core. That core flux is set up by this XM, that is called the magnetizing component of magnetizing reactance. This is actually responsible for the flux setup in the core. Then only the transformer will work. That is the heart of the transformer, right? Flux setup. So the basic requirement of transformer is nothing but a flux setup. The current which is responsible for that flux setup is called the magnetizing current, or IM. Or we can write like this: I0 is a vector which is nothing but IM plus IW. Both are vectorial addition. And the magnitude of I0 is nothing but IM square plus IW square. Very, very important. IM square plus IW square. Very, very important. Very, very important. And you can draw the phasor diagram using these components. I will draw that also. Phasor diagram on no load. So this is nothing but phi m. This is nothing but I0. Sorry. I0. It having two component. One is IM. This is phi 0 and this is called IW, and this is nothing but V1. This is nothing but V1. This is nothing but V1. And if some load is there, or not there, no meaning. This will be E1. Suppose this is a stepped up transformer, this is E2. So this is the phasor diagram on no load. Phasor diagram on no load. The same thing that we discussed earlier, but in addition to that, there are one more terms. What is that? This IW and IM bus. The phi 0 is nothing but the angle made by this I0 with respect to V1, which is very, very important. Actually, normally we take these angles are like this now with respect to horizontal, but here it is in with respect to vertical. That is very, very important. Or there are two components of this I0, one along the horizontal, which is in phase with this phi m is nothing but IM, and other is in quadrature with that IM, which is called IW. Or we can say that IW are simply V1 into IW are simply I0 cos phi 0, and IM is nothing but I0 sin phi 0. You know this, right? IW is equal to V0 I0 cos phi, and IM is equal to I0 sin phi 0. And I already told you that there is a heat loss in the core of the transformer on no load. The responsible heat loss responsible for that heat loss component is that V1 into I0 cos phi 0. This much what is the heat loss there? Because heat is nothing but the voltage into in phase component, right? In phase component is nothing but I0 cos phi 0. So V into I into cos phi is nothing but what? And the power required for the setup of flux, right? Power required for flux setup in the core is nothing but what is that? V1 into I0 sin phi 0 volt ampere. This much volt ampere. This much volt ampere. This much volt ampere. And for this practical transformer, the value of phi 0 is nearly 75 degree. For practical transformer, the value of phi 0 is nearly 75 degrees, so that cos phi 0 will be nearly 0.25 range or nearly very low. So this also you have to note. The practical transformer phi 0 is very low, actually very high. This much will be the phi 0, so that angle will be for cos phi 0 will be 0.25. That you have to note. For ideal transformer, what will be the value of phi 0? 90 degree. Am I correct? That means for practical transformer there is no loss, right? There is no loss means there is no IW. There is no IW means simply this I0 lies like in the horizontal manner. Or we can say that the angle between V1 and I0 is to be termed as the power factor, right? So the transformer angle will be at that time phi 0 will be 90 degree, or I can say that power factor is equal to 0 lag. Power factor will be equal to 0 degree lag, because cos 90 is nothing but 0. So 0 degree lag will be the power factor for what? Ideal transformer. For ideal transformer. Okay, so that's all about the session. And from this figure, power factor is said to be power factor equal to cos phi 0, which is nothing but opposite side divided by hypotenuse, right? Opposite side is nothing but Im, hypotenuse is nothing but I0. Im by I0. That also you can refer from there. Im by I0. So that's all about the Phasor diagram of transformer or no load. Okay. So that's all about today's session. Let's meet again tomorrow. Okay. So thank you.